Hello and welcome to this video. In this video we're going to be looking at the properties of atoms. So at GCSE we should already be familiar with the general structure of the atom. So we should know that the atoms have a nucleus. So this is the, I'm going to draw that over here. This is the nucleus of the atom, so the center of the atom, and the nucleus can be broken down into multiple things. So these things inside the nucleus, so the nucleus gets split into protons and neutrons, and then so some of these are positively charged because they're protons, and some of these will be neutral because they are neutrons. Now this is the nucleus in the center, which is positively charged because of all the protons, and there's no negative charges inside the nucleus to be able to cancel it out. And so where the negative charges come in is we have energy levels or shells which house electrons. Okay, so let's say this is a few electrons, and those of you who are also doing GCSE chemistry will be able to recognize there's the 2A8 rule, where we need to fill up specific energy levels with specific amounts. When you get to A level, you'll learn that what we're actually filling here are called orbitals. Okay, but that's for the chemistry thing. But it's the same rule applies, since all of your A levels is just teaching you knowledge. It's not necessarily specific to a subject. And these things here are electrons, and these lines represent energy levels. Okay, this is what we call the Bohr model. Okay, so the Bohr model says that we have a nucleus in the center that we know from Rutherford's scattering, which we will look at when we come to do nuclear in A2 in more detail. But Bohr model says there is a nucleus in the center and there are electrons that orbit in non-radiating circular orbits. Okay, what they mean by non-radiating is just as something travels in a circle, or as an electron travels in a circle, it will naturally give off some sort of radiation, which means it should lose energy and eventually be attracted towards the positive nucleus. But one of the postulates of Bohr's model is that that doesn't happen. Okay, so this is the Bohr model. This is not the accepted model anymore, but we're going to use it just to simplify a few things, because it can still be used to help make some of the more complicated ideas look a little bit simpler. Okay, so this is the Bohr model, which we're familiar with. We know we've got the nucleus in the center. Now the nucleus actually would be a lot smaller than I've drawn it here, but this is just so I can basically expand it to show the size of the protons and neutrons, surrounded by the energy levels which are filled with electrons. Now, to give a size comparison of this, the average radius, so from the very center, the nucleus, out to the edge, this radius, so the average radius of an atom is about 10 to the minus 10 meters. Okay. This is also known, for those of you who are more interested, you can also call this this symbol here. This is the same as saying A with a little circle on it. This is known as an angstrom. So if you're ever researching it and find across this unit, just know it's literally just 10 to the minus 10 meters, and it's named this, or it's been defined as this because this is the average radius of an atom. In comparison, we can get protons. If we take an individual proton, that would be maybe 10 to the minus 15 across. So it's 10 or 100,000 times smaller than the size of the atom. So it's actually more like a pinpoint in comparison to this, what I've drawn here. Okay. Now, so the important things that we need to know are the fact that there's protons and neutrons in the nucleus and we have electrons in energy levels. The rest of this stuff is kind of extra knowledge to try to help you bridge the gap between this and A level. But then we need to know some properties of protons, neutrons, and electrons. Now at GCSE, you would have been told that protons, neutrons, and electrons have some sort of relative charge, which I'm just going to put as relative Q, because we know Q now is charge at A level. They also have some relative mass, and we've already discussed the location that they're found in. So protons and neutrons in the nucleus, electrons in energy levels. Now what we would say for these things is that the relative charge on a proton is going to be a +1. Now there's a key word here, and it's relative. Both of these things are relative. If we're trying to actually measure a charge or actually measure a mass, we can never say like the mass of this pen is 5 nothing, right? We have to express some sort of unit. These are relative, so they don't express a unit. They're just how much charge do they hold compared to each other, right? So we define the proton to be the most stable one, and so we compare everything to the proton. So the proton has a +1 charge. It also has a relative mass of just 1. The neutron is neutral, so it has a 0 charge, and has a relative mass of also 1, because they have the same mass. Now electrons have a relative charge of -1 and a relative mass of 1/2000, okay, or 1/1860 if you want it to be more specific, but you can get away with 1/2000 at A level. Now, this is GCSE. We're going to abandon this for now. Okay, we're going to say all of this is true as long as we're looking at relative masses and relative charges, but we're no longer interested in looking at how they compare to each other. We now want to know what's the actual charge of a proton, what's the actual mass of a proton. And so this is where we're going to bring in some data. Okay, this can be found on your formula sheet, but it would do you well to be able to be doing as much practice so that you can commit these things to memory. So by the end of the first year, at least, you should know these values off by heart. Okay, and what we're going to do then is let's start this again. We said we need to know protons, neutrons, and electrons, and now instead of saying it's a relative charge, it's just charge, and that means we need to put a unit, and the unit of charge is coulombs, which we're just going to note as a C. Okay, and the mass with a unit as kilograms. Okay, so these are what are known as our SI units. Okay, SI units is just a French system for units where we can have loads of different values and they have different units. So we have decided on the SI units, which we're going to go through in another video, that is going to decide the most common unit system so that we can agree on the numbers without having to do all these conversions and stuff. So all charges that you'll meet should be in coulombs and all masses should be in kilograms. Okay, now protons have a charge of +1 relatively. This is going to become plus 1.6 times 10 to the minus 19 coulombs. Okay, this number is going to come up a lot because it's used in not only the charge of this, but it's also, since the electron is going to be negative the same charge, minus 1.6 times 10 to the minus 19, it's used in defining some units. And it's just going to be overall a good number to memorize. But neutrons are neutral, so they still have 0 coulombs worth of charge. Now, protons have a mass of 1.673 times 10 to the minus 27 kilograms. Neutrons have a mass of 1.675 times 10 to the minus 27 kilograms. and electrons have a mass of 9.11 times 10 to the minus 31 kilograms. So, to clarify, the masses of protons and neutrons are not exactly the same. Okay, neutrons are slightly heavier than protons, but only by 0.002 times 10 to the minus 27. So that's 2 times 10 to the minus 29. So you have, or 30. So you have basically a very, very, very small difference between the two of them. But for most calculations, so when you're looking at things like specific charge, or just looking at the masses of protons and neutrons, you can treat them as just being 1.67 times 10 to the minus 27 to make it easier for you. This brackets for the 3 and the 5 is how it's written in the formula sheet, because in the formula sheet, they don't expect you to apply this to calculations, but they expect you to know that there is a slight difference between the two of them. This is going to help when we're explaining things like beta minus decay or beta plus decay, because we know in beta minus decay, this neutron is going to decay into a proton, releasing an electron. So if we're forming an electron, we can't just be pulling mass out of nowhere. So the mass is the difference, the tiny difference from here is enough to pull out an electron. And we'll find that it also pulls out anti-electron neutrino as well. Okay, and the mass of the electron that we find is still almost 2,000 times smaller than the mass of the proton and neutron. Okay, so this is everything that we absolutely have to know about the nucleus. You need to know its all the things it's made up of, its structure, the charge of all of those things, and the mass of all of those things. These values, again, on your formula sheet, but I would recommend doing enough practice questions so that you just know these things off by heart, and that way in your exam you don't have to waste time going through the list of all the data. You just know the value and can recite it like that. Okay, so hopefully this clears up a lot of things. Thank you for watching.